Hey everybody, welcome to notes number 3.2. Our third unit continues with the normal distribution, but now we're going to work backwards. So in our last lesson, we looked at, okay, if I have my x, if I have my mu and my sigma, I can find z, and I can use that to calculate probabilities. Well, in this lesson, we're going to work backwards. If I know the area or the probability, can we back it up to our z, and from z back it up into our x, our mu, and our sigma? So continuing the conversation means we're continuing the normal distribution. Remember, we're bell-shaped. Everything is based off of the mu, the mean, and the standard deviation, sigma. We still have that total area under the curve equaling 1, and x is still a horizontal asymptote. So remember, there are unlimited number of these because every time the mean is slightly different or standard deviation is slightly different, that means my curve is a little different. And so we're going to continue standardizing this with our z-scores, and we will need to work backwards. So if I'm trying to find the values, aka I'm trying to find the x given a probability, then first we're going to use that probability to find z. Now, please be aware that when we do this in the calculator, I have to first make sure the probability is set up as area left because the calculator only knows or understands area left when I'm working backwards. But if you have the area left, then there's this thing called the inverse normal distribution that allows me to back up and find the z-score. If I know the z-score and the z-score formula, I can then find my missing x value. So essentially, we're going to work backwards. Calculator-wise, we're still going to second vars, but now we're going to use the INV, the inverse norm, and it's going to ask you for the area. Make sure you are using the area with four decimals when you can. So, also again, reminder, this area is specifically area left. That is assumed to be area left. So example 1, what z value has an area of 0.7357 to its left? Well, just like we did in our last lesson, the first thing I want you to do is sketch your normal distribution. Gives you a picture of something to look at. Now keep in mind, if I'm here in the middle, then I've got 50% area of 0.5 on the left, area 0.5 on the right. So if they're giving you an area that is bigger than half, that means we need to be bigger than 0. Now I started to make our little dashes, but here's the problem. I don't know where that z-score is going to fall. They didn't give me z. Instead, they asked me for it. What z value will give me the area, the shaded area, left to be 0.7357? I just know it's going to be on the bigger side because I'm bigger than half. So what I have to do, if my area left is 0.7357, remember with our standard score, the mean is 0 and the standard deviation is 1. And in order to work backwards, I'm going to use the inverse norm. Now in your calculator, the inverse norm first wants your area left, 0.7357. Then it's going to want your mean, 0. Then it's going to want your standard deviation of 1. And just like we've done in our last lesson, in order to get there, I'm going to go second vars down to inverse norm. Now my calculator pops up these options. If yours doesn't, then you would fill them in on the home screen. My area is 0.7357. Mu is 0, sigma is 1, and it spits out. This is now the z-score. Remember that z-scores use 2 decimal places. So this z is 0.63. My z-score, 0.63. One of the things you're going to have to be careful on is making sure that you're using kind of your critical thinking skills to decide, hey, if I'm bigger than half, I better be on the positive side. Right? If I'm less than half, I'm probably going to be on the negative side, and use that to kind of help reason your way through. Does this answer make sense to us? Let's try another one. What z-value, aka z-score, has an area of 0.0096 to its right? Sketch it first. I'm looking for a very small area to the right. If 0's in the middle, with it being small, that means I'm somewhere over here. I need a small right-sided shading. In the last one, I had a big left-sided, so I went over here to the right side. Now I want a small number in the right side, so I should only be shading a small amount to the right. My z should be somewhere over here. Now here's the problem. My calculator only knows area left. Well, here's the beautiful thing about left versus right. Area left and area right of z are complements. Remember what that means from probability. That means area left is the same thing as 1 minus area right, because the total area under this curve is 1. So in order to find the area left that I need, that's 1 minus my 0.0096. 1 minus 0.0096 is 0.9904. That's what I'm going to use for area left. So in my calculator, area left of this same z is 0.9904. Using that total probability of 1. So since I'm working backwards, since I'm asked for z, I'm going to use inverse norm. Area left, mean, and standard deviation. This is going to spit me out a z-score. So second vars down to inverse norm. Area is 0.9904. Mu, sigma, paste. Remember to round to 2 decimal places for our z-scores. 2.34. So this z is 2.34, a little more than 2 standard deviations above the mean. Good. Let's try bringing in some other words from some of our previous lessons. Example 3. What z-value represents the 90th percentile? Ooh, we haven't heard that for a while. Remember that the percentile is a value such that blank percent is at or below that value. So what they're really asking me here is to find the z-value. Actually, let me sketch it. It'll be easier to see it on the curve. What they're asking me for is a z such that 90% of my data is below it. AKA my area left is 90% or 0.9. So when they give you percentile, they're automatically giving you the area left to be 0.9. So I can go into my inverse norm. I don't have to do any extra work. 0.9 is my area, 0 and 1. And this is going to spit me out a z-score that has an area left of 0.9. Because this is at or below, this is automatically area left. So 0.9, 0, 1, 1.28. My z-score is 1.28. Good job, everybody. Let's do just a couple of more. Ooh, area between. This one's going to take a little extra work for us because area between and area left are definitely not the same. So let's remember from our previous lesson, if they're looking for area between, then I have to have two z-values, my first z and my second z. So that here in the middle is 0.9. Now, please keep in mind, this is not the same as the percentile we saw earlier. Percentile is below, all the way below. This is asking me for 0.9 to be in between two values. Now, here's the nice thing about the normal distribution. It is symmetric. So if I need area left, I need the area left of that first z-score. Once I have the first z-score, I'll be able to use symmetry to know the other one. So in this type of example, the first thing we need to do is use complement to find the area outside in the tails of my curve. So I'm talking about finding these two tails. Well, the area in the tails, the area outside, is 1 minus the 0.9 that's inside of my shading, giving me 0.1 split between these two tails of my curve. So I got rid of this. Now I'm just looking outside. Then area left is just half of that. So the second thing we're going to do is find area left by dividing by 2, cutting it in half. If I've got 0.1 between the two of them, when I divide it, I have 0.05 on just the left side. So if these together are 0.1, aka 10, when I cut it in half, that means I've got 0.5 over here and 0.5 over here. The joys of symmetry. That means I can look at just left as 0.05. And then when I go to that inverse norm, my area left is 0.05. So I'm kind of running out of room on my screen. 0.05, negative 1.648. Now, this is the only one. When your area between is 0.9, I'm going to have you round to 3 decimals. And we'll look at why that is more in the next lesson. But in this specific example, I do want you to round to 3 decimals, giving you z as negative 1.645. Thanks to symmetry, if this one is negative 1.645, then this one is positive 1.645. So your two z-scores are the positive and negative version of your result. That one was kind of a lot. Let's have you try example 5. Pause this video and try it. In fact, because this video is running long, I'm going to stop this video here, give you some time to try number 5 using that same process, let you think through it, and we will come back for one more video on this lesson.